All right, let's just jump right in. Imagine this. You've built an incredible website. It's a game changer. So good, in fact, that you go viral, and suddenly millions of people want to use it all at once. Now, that sounds like a dream come true, right? Well, it can turn into a total nightmare for your infrastructure, and fast.
So that's the big question, isn't it? What could possibly be the downside of that kind of massive, sudden success? The answer, and it might not be what you expect, has everything to do with how your users actually connect to your website.
You know, in a perfect world, it's super simple. One person on their laptop sends a request out, and boom, it hits your single application server. That server sends the website right back, and everything's fast, everything's snappy. It's a perfect, happy experience.
But what happens when 10,000 users try to do that at the exact same moment? Yeah, that one little server gets totally swamped. It's just drowning in requests. It slows down to a crawl, and eventually, it crashes. For your users, the experience is, well, let's just say it's very unhappy.
So there you have it. You've become a victim of your own success. Your website is just too popular for its own good. Now, the obvious thought is, okay, why not just get a bigger, beefier server? That's called vertical scaling, by the way. But here's the catch. You can't just make a server infinitely bigger. There are very real limits, both physically and financially. So that's not the answer. We got to think differently.
And that different approach is something called horizontal scaling. Instead of building one monster server, you just add more servers. Maybe you have 3, maybe 10, maybe even thousands, all ready to serve your users. Sounds like a great solution, right? Problem solved. Well, not quite, because this solution creates a whole new problem.
I mean, think about it. With all these servers sitting there, how does a user's request know which one to connect to? If they all just pile onto the first server in line, you're right back in the same boat, aren't you? You need something, or someone, to play traffic cop.
And that, my friends, brings us to the hero of our story, the Internet's traffic cop. This is the piece of technology designed to solve this exact problem. It stands in front of all your servers, managing the incoming chaos before it even has a chance to reach them.
And that traffic cop is the load balancer. It can be a piece of hardware or just software, but its entire job is to sit right between your users and your bank of servers. It intercepts every single bit of incoming traffic and intelligently distributes it across all of your available servers, making absolutely sure no single one gets overwhelmed.
Okay, so how does it actually do that? I mean, how does it make those decisions? It's not just pointing traffic at random. Nope. It uses specific strategies, or what we call algorithms, to intelligently decide exactly where each and every new connection should go.
And these strategies really run the gamut. You've got your very simple, direct methods to just follow a basic sequence. Then you have the really intelligent approaches that are constantly monitoring server health. And of course, there are plenty of options that find a nice, happy middle ground between simplicity and performance.
So let's dive in and check out these strategies. We'll go from the, let's call them simple, to the smart, and see how they determine the fate of every single user request that hits your website. And more importantly, which one might be the right tool for the job.
First up, the simplest of them all is called round robin. And honestly, the best way to think about it is like you're dealing a deck of cards. The first request goes to server A. The second, server B. The third goes to server C. And when that fourth request comes in, you're just back to the top of the deck. It goes right back to server A. It's simple, it's predictable, one after another.
But simple isn't always what you need, right? The huge weakness of round robin is that it has zero idea how busy each server actually is. So if one user starts a really intensive 2-hour-long session on server A, while other users have quick 5-minute sessions on servers B and C, well, server A can get totally overloaded while the others are just sitting there basically idle. The whole system gets out of balance.
And this brings us to a much smarter way of doing things: smart load balancing. In this kind of setup, the servers are constantly chatting with the load balancer. They're reporting back on how busy they are, maybe saying, hey, my CPU is at 90% utilization. The load balancer uses all that real-time data to send new traffic to whichever server has the most free capacity at that exact moment. Now, I know what you're probably thinking. Why on earth wouldn't you always use the smart method? It's a great question, and it really gets to the heart of all engineering: trade-offs. See, a smart load balancing setup is way more complex and time-consuming to configure. Plus, the hardware or the software you need is usually more expensive. For a lot of applications, it's just plain overkill.
And that's why we have a middle ground. This table here breaks down a few options that split the difference. A really common one is random select, where the load balancer just, you guessed it, randomly assigns traffic. By breaking that rigid sequence of round robin, it's statistically way less likely to overload one server with long sessions. But, and this is key, it's still a simple method that doesn't need all that constant server communication. It's a great low-complexity alternative to a fully smart system.
You know, this ability to intelligently manage traffic is precisely why the load balancer is such a fundamental, key component of modern cloud architecture. It's really the secret sauce that enables things like microservices to scale up and down on their own, and it powers one of the most cost-effective features of the cloud.
And that amazing feature is auto-scaling. Because the load balancer has its finger on the pulse of the whole system, it can make decisions for everyone. If servers are reporting back that they're only at 20% usage during a quiet period, it can automatically shut some of them down to save money. But then, if they're all screaming for help during a traffic spike, it can request brand new servers to be spun up instantly to handle the load.
And this isn't just an abstract idea. This is how it really works in the real world. In most systems, when servers consistently report that their utilization is hitting 85 or 90%, that's the trigger. The load balancer signals the auto-scaling service, and help is brought in automatically. No humans required.
So what's the big takeaway from all this? It's that load balancers are absolutely essential. They prevent your systems from crashing under a heavy load, they enable the cost-saving magic of auto-scaling, and they really do form the very foundation of how the modern, scalable cloud actually works.
They are truly the unsung heroes that make sure your viral success story has a happy ending. But this raises a whole new question, doesn't it? If load balancers solve the traffic problem so elegantly, what's the next hidden challenge you're going to face when you're building an application for 1 billion users?